How is software essential to the operation of a computer? The exam answer on trial. Okay, let's dive into this explainer immediately, and we're going to do it by putting a shocking piece of evidence literally under the microscope. We are looking at a huge fundamental question today. How is software essential to the operation of a computer? And to understand the right way to answer this, we're actually going to start by looking at a completely disastrous way to answer it. So consider this explainer your personal courtroom, and we are examining our primary piece of evidence right now.
Look at this generic student exam answer. This one sentence literally just costs someone their grade boundary. Why? Because it completely ignores the precise technical vocabulary the examiner is begging for. Software is apps that make the computer do things. I mean, it sounds like it makes sense on the surface, right? We all use apps. But in the context of Cambridge computer science, this sentence is a criminal offense. It lacks depth, it lacks precision, and frankly, it fundamentally misunderstands the entire architecture of a computer system.
So what does this all mean? Why exactly does this answer lose all its marks? Well, we're going to investigate exactly what went wrong here, and more importantly, how to upgrade it into a flawless, top-band response. We'll do that by uncovering the true relationship between software and hardware. We absolutely have to move past the everyday slang of apps and understand the invisible, complex layers of code that actually keep the machinery alive. Section 1. The investigation. System versus application software. To build our case, we first need to look at the fundamental divide in software types. You see, a computer system is made up of both physical hardware and digital software, and both are completely essential. But here's the catch. Not all software is created equal. There's a strict hierarchy you've got to know. First, you have systems software. This is the collection of programs and processes that a computer absolutely needs just to function at all. It controls the hardware. It's literally the life support system of the machine. Then, on the other hand, you have application software. These are the programs that allow us humans to perform specific tasks, like writing a document, browsing the web, or playing a game. So a computer relies entirely on system software just to exist, while application software handles the stuff we actually want to accomplish. Basically, if you don't have system software, your application software is utterly useless. Now, what's really fascinating here is a highly specific, kind of hidden type of system software called firmware. Firmware is system software that is embedded directly into hardware devices right when the computer is being built in the factory. An absolutely excellent example of this is the BIOS program. It acts as firmware installed directly onto the hardware components, meaning you, the user, never have to manually install it or mess around with it. It's just there, quietly working behind the scenes, making sure the hardware wakes up properly the second you hit the power button. Section 2. The operating system defense. Let's see how this builds into the absolute most critical piece of system software you need to understand, the operating system. If firmware is the spark that wakes the computer up, the operating system is the brain that takes over and manages everything from that second forward. It does the heavy lifting. It acts as the ultimate manager. It provides a vital line of defense, utilizing utilities like firewalls and authentication to protect your files. It handles user management, creating specific system, administrator, regular, and guest user accounts, which keeps everyone's data isolated and safe. But it goes way deeper than that. It manages the physical memory available in the system, rigorously allocating resources to the hardware so user instructions can actually be carried out without the whole system crashing. And it handles hardware interrupts, reacting in literal milliseconds when a piece of hardware demands immediate attention. But let's pause for a second and ask a much deeper question. How does software actually translate our human logical conditions into physical hardware actions? We know the OS manages things, right? But how does code actually make hardware do something? Well, to understand how humans use software to interact with devices, let's examine a highly practical scenario straight from the source material, a security light outside a house that is programmed to turn on if it's after 6 p.m. or if it's dark. Now, what's really interesting here is how normal human language breaks down into strict mathematical logic. Because remember, the computer doesn't understand dark or 6 p.m. It only understands Boolean values of true or false. So we take the condition, it is after 6 p.m., and give it a binary value of 1 for true. We take, it is dark, and give it a binary value of 1 for true. By pushing these inputs through a logic gate, the software mathematically determines the physical output, literally calculating whether the hardware should physically trigger the bulb to illuminate. It's wild. This is the invisible bridge between a software condition and a hardware reality. So we've seen how logic gates trigger hardware, But there is still a massive missing link. In a moment, I am going to show you the exact examiner clue that changes a passing exam answer into a perfect one. But first, you need the framework that makes that clue super obvious. Before we reveal the final verdict on our flawed answer from the beginning of this explainer, we must uncover the hidden mechanism that actually connects human programming instructions to that underlying hardware execution.
Section 3. Translators and Languages. The crucial point here is understanding how human developers actually communicate with these machines using programming languages.
Let's be real, humans don't write in binary ones and zeros. We need a way to talk to the hardware without having to speak its native, incredibly complex language. This creates a pretty obvious communication gap. We write software in high-level languages. These are human-readable, using English-like syntax and abstract logic that allows programmers to solve problems quickly. But here is the catch. The computer hardware has absolutely zero idea what a high-level language is. It only speaks low-level language, or machine code, pure binary that goes direct to the hardware. The human is speaking one language, and the hardware is speaking another.
So how do we fix this? Well, this step-by-step mechanism shows exactly how we bridge that massive gap. Step 1, the programmer writes the high-level code. Step 2, that code is fed into a specialized piece of system software called a translator. Step 3, the translator completely converts our human-readable logic into pure, low-level machine code. And finally, Step 4, the hardware receives the exact electrical signals it needs to execute the command. Without translators, application software literally could not run on computer hardware. It's that simple.
It's definitely important to note there are two main types of these translators. Depending on the specific software and testing needs, developers use either compilers or interpreters. A compiler is like a professional book translator. It takes the entire high-level program and translates it into machine code all in one go, producing a ready-to-run file. An interpreter, on the other hand, is more like a live UN translator. It processes and executes the instructions line by line, which is incredibly useful when developers are actively debugging and checking their code for errors. Section 4. The examiner's verdict. Armed with all this evidence, it is finally time to return to the scene of the crime. Let's upgrade our terrible student answer from the start of this explainer. Look at the incredible difference here. The weak answer relies on vague, everyday terms. But by replacing that generic fluff with precise, Cambridge-safe nouns, we transform a zero-mark failure into an absolute high-scoring masterpiece. The top-band answer states clearly, system software manages hardware operations, while application software utilizes translators to execute high-level user tasks. Boom. Do you see how that proves to the examiner that you understand the hierarchy? It proves you know that software isn't just one thing, but a layered system working together to control hardware. These are the exact technical terms you must use in your exam scenarios to demonstrate that you truly understand how software is essential to computer operation. When you look at a question, don't just think software. You've got to think about your arsenal. Is this a question about firmware embedded at manufacture? Is it about the operating system managing interrupts and memory? Is it about translators bridging the gap between high-level human logic and low-level machine execution? Using these exact terms is absolutely what guarantees you those crucial marks. Okay, so we've thoroughly established exactly how system and application software cooperate to keep a computer alive and functioning. But wait. This actually introduces a terrifying new vulnerability. Think about it. If system software like the operating system has total, unmitigated control over the hardware, user accounts, and memory, how do you protect these essential software systems from malicious network attacks? Because leaving this unresolved leaves your exam and real-world systems completely vulnerable.
Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations.
Now that you understand the software architecture, your mandatory next step is learning exactly how to defend it. Click on this next explainer right now to master the exact cybersecurity skills required for Paper 1. Because honestly, what good is a perfectly functioning operating system if it takes just one malicious attack to bring the whole thing crashing down?